Hello everyone, my name is Tanisha Sharma today I am very excited to present my project, the Smart EV ADAS dashboard. I developed this project during my internship at MITech's Information Technologies in Bangalore. It was a fantastic learning experience that allowed me to bridge the gap between embedded software engineering and real world automotive safety. This project is a comprehensive ecosystem that simulates an electric vehicle integrated with an advanced driver assistance system (ADAS). It features a hardware layer running on a STM32 Bluepill microcontroller, emulated using PiximLab, which communicates in real time with a dynamic custom-built Python GUI dashboard on a PC. The system continuously monitors critical vehicle data like speed, battery, temperature, and state of charge while simulating evaluating safety hazards like forward collision and blind spots. What is EV ADAS? Driving safety. ADAS helps drivers stay safe by automatically watching the road for obstacles. Made for EVs. In electric vehicles, ADAS also tracks battery levels, range, and motor power dynamically. Smart displays. It alerts the driver about the danger using screens, buzzers, and flashing lights in real time. Now, system architecture. To keep the implementation structured and efficient, the system architecture is broken down into four core columns: sensor and inputs, the controller, networking and communication. We use analog potentiometers to stimulate physical inputs in the accelerator pedal, brake pedal, and motor temperature, along with the ultrasonic sensors to detect surrounding obstacles in sensors and inputs or stimulated inputs. The controllers. For the core brain of the system, we use the STM32F103C8T6 Bluepill microcontroller powered by an ARM Cortex M3 core running at 72 MHz. It processes vehicle physics, calculates distance measurements, evaluates diagnostic fault rules, and coordinates system alarms. Networking and communication or UART telemetry. Data moves between the microcontroller and the PC via high-speed UART serial communication over the UART1 peripheral. It is configured to run at 11522200 sorry 115200 baud rate, sending out updated telemetry packed every 100 milliseconds. Fourth one, the display or Python dashboard. On the PC side, a live Python dashboard built using Matplotlib. The incoming serial data streams and dynamically visualize goals, safety indicators, and environment tracking. The 9 project development phases. To ensure a robust system, the entire development workflow was organized into 9 structural phases, executed step by step. Phase 1 and 2. Setting up the STM32 Cube ID environment, configuring PiximLab, initializing the GPIO pins, setting up a PWM channel for an active warning buzzer, and stabilizing hardware timer interrupts. Phase 3 and Phase 4. Configuring the ADC channels to read potentiometer data, transforming raw voltages into throttle brake and temperature parameters, then coding the core EV math, simulating real-time vehicle speed calculation, battery state of charge, drainage under acceleration, and energy regeneration during braking. Phase 5 and Phase 6. Integrating the ultrasonic sensor logic to monitor forward collision threats and blind spot detections, building a diagnostic fault checking module that uses a bit field flag to track issues like over temperature or critical battery drainage, driving a 4-level safety alarm matrix. Phase 7, 8, and 9. Structuring the dual line telemetry transmission packet protocols, implementing an interactive serial command shell, aligned terminal overrides, and finally coding the complete Python application to parse these live strings and update the physical or graphical user interface smoothly. Now, end-to-end process workflow. First, read ADC converts potentiometer voltages. Second, EV update calculate driving physics every 10 milliseconds. Third, ADAS scans radar and sensors every 100 milliseconds. Fourth is triggered HC launches trigger pulses. Fifth, measure echo capture returning sonar waves. Sixth, computer TTC measures crash and blind spot risk. Seventh is set alarm decides severity level from 0 to 3. Eighth is buzzer alert generates active warning frequencies. Ninth, UART frame packs telemetry values into strings. 10th, UART 1 send pushes frame serial wise at 115200. Word plot. PC read Python parses comport bytes. 12th is regex parse extracts signals clearly. Sync states update PC dashboards dictionary. GUI redraws screen dials at 10 FFC. Now software implementation. We developed the project using STM32 Cube IDE. The .ioc file is used to configure GPIO pins, UART, and clock settings. After saving it, STM32 Cube IDE automatically generates the initialization code. The main program is written in main.c. It initializes all peripherals, reads sensor values, processes ADAC logics, and continuously sends data to the Python dashboard through UART inside the file1 loop. After this, we use soft hardware implementations. In this, we use Bluepill STM32 F103 C8 T6 PixMLab. This spare parts at the left side contains sliders for acceleration, brake pedal, battery SOS, and motor temperature. At the top, there are three ultrasonic sensors for front, left, and right. Obstacle detections. LEDs indicates warning conditions and buzzers give an alarm whenever an obstacle comes too close. The virtual terminal continuously displays UR data such as speed, battery, distance, alarm, and fault. After all fixing configurations, we use command prompt. Now let's look at the software side execution on our host computer. Here I have opened command prompt pointing to our workshop folder. We initiate our custom UI application by executing the script using the commands python ev-py port com1. As you see instantly in the log, the application safely initialized a serial link showing UART connected com1 @115200. This confirms that the Python application is now reading real-time bytes from the PixMLab microchip at a fast baud rate. Once running this dark theme analytical dashboard is generated, let's break down the visual widgets, speed dial, and history graph. On the upper left, we have a circular speedometer gauge displaying the live speed which is currently at 20 km/h. Directly underneath the speed history graph plots the speed waveform against time dynamically to track continuous acceleration patterns. Battery status SOC. Right at the center top, the dashboard reads the high voltage pack status currently sitting at 99.9% battery, a solid green bar is given as an immediate visual feedback of the charge level. EV telemetry metrics table. In the middle block, we parse as display exact vehicle state numbers, torque, acceleration, brake, motor temperature, alarm, fault, and signal. And at another corner, we have a dash bird eye, in which if I move the front obstacle closer using the ultrasonic sliders, the display distance decreases at the same time the TTC value also decreases. Now, if I decrease the front distance, this means the obstacle getting closer to the vehicle. As a result, the TTC decreases and dashboard displays a collision warning like this, and alarm so critical. Now I am increasing the front distance. The obstacle moves further away, the TTC increases, and the warning, one second, the warning disappears. Now I am decreasing for left and right distances. Now I am decreasing the left distance and the right distance. This indicates an object or another vehicle is entering the left and right blind spots. Therefore, the blind spot detection warning is activated. Now I am increasing the left and right side distances, which makes the blind spot disappears. Now conclusion, final project results. One final component that provide incredibly helpful for automated validations is the interactive command shell process. By opening a secondary terminal window, we can input commands like SOC 50 or temperature 95 to manually inject critical fault values. This allows us to fully stress test our embedded safety codes and alarm systems instantly without having to manually twice tweak physical hardware ports. In summary, this project showcases a complete embedded ecosystem combining hardware timing controls, reliable serial port protocols, and intuitive graphical data visualization into a functional safety framework fit for modern electric mobility. Now, at last, thank you so much for your time. Thank you very much.